Hello and welcome to this Python tutorial. Alright, so we have one last function to implement in our replay memory class. That's the sample function, and that's of course to get some random samples from our memory, and therefore this function will return these random samples. Alright, so let's implement it. We are going to call it sample. Here we go, and this function takes two arguments as input. The first one, as usual, self, our future object of the replay memory class. And the second argument is, can you try to guess? Well, we're taking some samples, a fixed size, and therefore we need to choose a size for our samples. And more precisely, we call it a batch size. So that's the name we're going to give to our second argument, batch size. And there we go, we have our two arguments, and now we can implement the sample function. So now I just want to warn you, this is going to get a little technical, but I'll try my best to explain. So we're going to start by creating the samples variable. This is just the variable that will contain the samples of the memory. Alright, so samples equal, and so now how are we going to get these samples? Well, first of all, we have to take our memory, because we're getting these samples from our memory. Then we will probably need the batch size, because the samples we want to get contain batch size elements. So we need memory, we need batch size, and then we need some PyTorch or Python tricks to get the good format of these samples. So what I'm going to do, I'm going to write the line of code, and then I'm going to explain it element by element. So let's do it. I'm starting by taking a zip function. I'm going to explain very soon what it does. And inside this zip function, I'm going to add a star. I'm going to explain that as well. A star and random.sample. So random, as you might have guessed, is the random library that we imported here. So that's the main reason why we had to import this random library. It's because we're taking some random samples. So from this random library, we're going to use the sample function. So this is our variables, and this is a function. So I'm going to add some parentheses. And now, as you can see, sample is a function, and we have to input some arguments. So as you can see, the first argument is self. And actually, speaking of self, this corresponds to self.memory, the memory of our future instance object of our replay memory class. So I'm going to add here self.memory. And then the second argument is, as you might have guessed, the size of the batch we want to take randomly from our memory. And that we gave it a name, that is batch size. So the second argument is going to be batch size. All right. So the line of code is typed, and now I'm going to explain what it does. So first of all, with this random.sample function, we're taking some random samples from the memory that have a fixed size of batch size. So that's understandable. But then what does this zip star function does? Well, there is no mystery about it. It is just like a reshape function. So for example, I'm going to add a little comment here just to explain, then I'm going to remove it. So let's say that, for example, we have a list of the following elements. For example, first 1, 2, 3, and then the second element 4, 5, 6. So we have a list of two tuples of three elements, 1, 2, 3, and 4, 5, 6. Well then, if I apply the zip function with the star on it, well, what will it become? So zip star list is going to be equal to a new list, but of a different shape. And this different shape is going to be 1, 4, then 2, 3, and then 5, 6. All right, so that's just what it does. It just reshapes your list. Okay, so now that you understand what this zip star list does, well, now let's explain why we have to do it. So, as you understood, we're going to add the events to the memory. And the events have the form, first the state, then the action, and then the reward. But for our algorithm, we don't want this format. We actually want our samples to have the following format: a format composed of 3 samples, 1 sample for the state, 1 sample for the actions, and 1 sample for the reward. So for example, let's say that this 1, 2, 3 is state 1, action 1, reward 1, and then state 2, action 2, and reward 2. Well, what we want is one batch for each, one batch for state 1 and state 2, one other batch for action 1 and action 2, and a third batch for reward 1 and reward 2. That's just the format that is going to be expected next, because then we will wrap these batches into a PyTorch variable. And a PyTorch variable, remember, is a variable that contains both a tensor and a gradient. And that in order to be able to differentiate with respect to a tensor. To be able to differentiate with respect to a tensor, we need the structure of a variable containing a tensor and a gradient. Again, that's how PyTorch works. So to summarize, we're creating one batch for each of the states, actions, and rewards, and then we're going to put each of these batches separately into some PyTorch variables, which each one will get a gradient, so that eventually we'll be able to differentiate each of them. Alright, so that's the purpose of this zip function. So let me just remove this comment, and now the only thing that we have to do left is to return the samples. So as I just explained, we cannot return the samples directly for the simple reason that we want to put the samples into a PyTorch variable. So to do this for each of the samples, we're going to use the map function, and this map function will do the mapping from the samples to torch variables that will contain a tensor and a gradient. So as you can see, this map function takes several arguments. The first argument is a function, and this function is going to be the function that will convert the samples into some torch variables. And the second argument is what we want to apply this function onto. So that will be the argument of this function. And therefore, what is it going to be? That's of course going to be the samples. So the second argument here is going to be the samples. But then let's define the function on which we want to apply each of the samples. So to define a function here, we need to first give a name to the function, which we'll call lambda. That's just a name I'm giving. Lambda, then x, which is going to be the variable of this function. So that is just a name I'm giving for the variable. And then colon, and here we give the expression of the function. That is what we want this lambda function to return. And so what it is going to be? Well, it's supposed to be something that will convert our samples into a torch variable. And to do this, we already mentioned it in some previous tutorials. Well, we have the variable function for that. The variable function will make that conversion from a torch tensor to a variable that will contain this tensor and the gradients. So the first thing I'm going to add here is variable. Variable inside of which I'm going to convert x, because x is going to be the samples once lambda will be applied onto the samples. But then that's not all. There is one last technical thing that we need to implement. It is the fact that for each batch which is contained in the sample, for example the batch of the actions, A1, A2, A3 and the other actions, we have to concatenate it with respect to the first dimension, which corresponds to the states. And why do we have to make this concatenation? It's just for everything to be well aligned. That is, that in each row, the state, the action and the reward corresponds to the same time t. So that eventually we get a list of batches all well aligned, and each batch is a PyTorch variable. So how can we make this concatenation? Well, we need to use the cat function from the torch library. So we're going to add here torch, to which we add dot cat applied to x. But then in this cat function we need to specify the dimension with respect to which we want to make that concatenation. And as I just mentioned, this is the first dimension that has index 0. And here we go, we have our function ready. This lambda function will take the samples, concatenate them with respect to the first dimension, and then eventually we convert these tensors into some torch variables that contains both a tensor and a gradient. So that later when we apply stochastic gradient descent, we will be able to differentiate to update the weights. Alright, so this function is ready, and then here, as the second argument of the map function, we need to specify onto what we want to apply this lambda function, and that is on all our samples. There we go. We will apply this lambda function on all the samples so that eventually we obtain a list of batches where each batch is a PyTorch variable. Alright, so that was quite technical, but now at least everything will work well. We won't use this technique afterwards, we only use it here, so if you don't want to have a deep understanding of the technical details here, well, that's fine. You can just copy these 3 lines of code to sample your memory if you want to make an artificial intelligence with PyTorch. It's as you want, but now the good news is that we are done with this replay memory class. Experience replay is now implemented, and we can move on to the next and final class, which will be the whole deep Q-learning model. So in this deep Q-learning model, we will have, of course, our network. We will add experience replay, and then all the rest of the deep Q-learning algorithm. So it's going to be a much bigger class. We're going to make about 10 functions, but that's only because we're doing this step by step so that you can understand better what's going on. So I can't wait to implement our deep Q-learning model, and until then, enjoy AI!